Welcome to this part of the video. In this video, I will be discussing about some of the applications of microwave engineering. So first we will see that based on the communication and non-communication, what are the different applications of microwave engineering. Now what do you mean by communications and non-communications? So basically communication means where a two-way communication happens, you send some data or receive some data, and non-communication means it is just a application, there is no communication happen between two ends, or there is no source or destination there. Okay, so based on the communication, first is communication network system such as high speed home and business networking devices like your Wi-Fi modems and routers, all those things. Then device to device communication is there, for example walkie talkies, and like massive MIMO technology is also there, and cloud technologies and small cell access points. Okay, cloud technology know that it needs internet connection, and through microwave signals only it is happening. And then device to device connection, as I said, your walkie talkies and your Wi-Fi modems. How do you access your Wi-Fi at home and organizations like this. Then communication devices, test instruments. Okay, so communication devices and test instruments such as what? Such as spectrum analyzer. So spectrum analyzer is a device which analyzes the received microwave signal. So that is a device. And then RF power meter. So these are the on side of the communications, means these are used, the devices that are used for communication to analyze those things. This spectrum analyzer, RF power meter, frequency counter, or some case it is called as frequency meter as well, signal generator and vector network analyzer as there are the application in based on communications. Next is navigation system such as GPS. Everybody is using GPS on their Google map and all, so this is a application of communication system. Why communication? Because your means mobile antenna is receiving signal from the satellites, then it is processing that, so basically it is receiving some information, so that's why it is come under the communication type. Then traffic light control. So in India it is not there, but in foreign this microwave signals are used to control the traffic lights as well. Then airborne radars and satellite communication. Airborne radar means the radars which can detect the objects from the air and all. Next, wireless remote control, and nowadays the the TV remotes are not coming with the IR sensor. It comes with the wireless like microwave RF system. Now, microwave engineering is used there. And then healthcare systems such as automatic gate door, automatic barrier systems, burglar alarms, and industrial automation systems, industry 4.0. In these all the cases your microwave engineering is used. Similarly, in non-communication, what is there? So sensors for industrial, agriculture, food and medical processing such as moisture measurement, ripeness or storage period determination, fruit sweetness detection, control of milk lime, monitoring of nitrogen, phosphorus. So like this, all these chemical factors of any agricultural product can be measured through microwave imaging, or we say microwave technology also. Means say food is ripe or not, that can be checked through the microwave signals. Next is heating, drying, freeze drying process, sterilization in food industry. So the best example is your microwave oven that is used in the kitchen as the non-communication application of microwave engineering. So that we will also learn towards the end of this lecture series. Okay, so heating, drying and all these applications can be the applications of non-communication based microwave engineering. Okay, next, industrial heating application. As I said that microwave oven at home and industrial also the same thing is there. And next is medical applications like hypothermia treatments, bioimpedance instrumentation, and medical diagnosis like MRI is application of these microwave signals. So these are some of the applications which are based on communication and non-communication types. Okay, next we'll see some other applications. So before that, I want to discuss something. Why standard circuit theory cannot be used directly? So why? What is the problem there, and why we need to read the microwave engineering as a specific subject? What is the need of that? So basically, because of the high frequencies and short wavelengths. So what does that mean? When the frequency is increased, the wavelength decreases. So they are inversely proportional to each other. Okay, frequency and wavelength are inversely proportional. Standard circuit theory often cannot be used directly to solve the microwave network. So what is the reason? Because of the short wavelength. So frequency increases then short wavelength is there, that means the wavelength becomes very less. What happens because of this? So this is due to the fact, why it happens, why it cannot be used. This is due to the fact that the lumped circuit elements approximation of circuit theory may not be valid through the RF microwave frequencies. Okay, lumped element means these are obviously some multiple devices connect to one node or something like that. So lumped circuit cannot be used here. So in microwave, what happens, instead of lumped we use distributed element. That will come, that you might have learned in the transmission line also, distributed elements. So microwave components often act as distributed elements, as I have told now, where the phase of the voltage and current changes significantly over the physical extent. That means, let's say there is a resistor is there. So if you see in your labs also, you will get some similar size of resistor as well. So if high frequency and short wavelength, so I can say if frequency is in gigahertz, then the wavelength will be this much of length. Okay, so this is physically this is the wavelength of a signal, this much of length only. And throughout the resistor, you see at very small distance the value is changing. That is what written here. Distributed, where the phase of the voltage and current changes significantly over the physical extent of the device. Okay, because the device dimensions are on the order of the electrical wavelength. So that is the problem here. So whatever resistor size we are using in normal AC circuits, the size of the resistor is somehow similar to the size of the wavelength. So that is why throughout the resistor the voltage is not constant, it is throughout the resistor the voltage is different. From here you can see. So this is the reason this normal circuit elements cannot be used in your microwave engineering or high frequencies. Next is, at much lower frequencies the wavelength is large enough that there is a insignificant phase variation across the dimension of the component. That means if here the phase is something, after some distance the phase is some difference, and after a distance the phase is again 90 degree. From 0 to 90 degree phase it covers in the small distance. So it is very difficult to analyze this kind of circuits. The other extreme of the frequency can be identified as optical engineering, in which the wavelength is much shorter than the dimension of the component. Okay, the other extreme of the frequency identified as optical engineering. So at the higher end, when it goes to the terahertz range, then the property is mimicked by the optical ray properties. Okay, whatever the optical characteristics is there of a wave, that is applied to the microwave signal. So that's what happens in the higher frequency. So these are some of the reasons why your circuit theory cannot be used directly in your microwave engineering, but it can be used with some proper modifications that we are going to see in the next unit. Okay, now there are we'll see the what are different applications. We have already discussed some applications in brief, and we will discuss the applications in a length. Okay, so antenna gain is proportional to the electrical size of the antenna. At higher frequencies, more antenna gain can be obtained for a given physical antenna size. So this is one of the applications why higher frequency microwave engineering used. Microwave signals travel by line of sight and are not sent by the ionosphere. Sorry, not bent by the ionosphere as are lower frequency signals. Okay, so what happens? There are some signals which reflect back from the ionosphere. So when it comes to that, I will explain that. And satellite and terrestrial communication, so with very high capacities, therefore it is possible, because in particular frequency ionosphere doesn't reflect the signal, it passes it. In some cases it reflects on some particular frequency. Then various molecular, atomic and nuclear resonances occur at microwave frequencies, creating variety of unique applications in the areas such as basic science, remote sensing, medical diagnosis, treatment and heating methods. Okay, so these are discussing what are the reasons behind the use of the microwave engineering. Okay, so we'll see that also different applications. So more bandwidth directly related to data rate. More bandwidth means if more frequency is there, then your data rate means the speed at which the data can be transferred will increase. So more bandwidth can be realized at higher frequency. At 1% bandwidth of 600 megahertz, if I say 600 megahertz frequency is there and only 1% of bandwidth is taken, then that comes to 6 megahertz. Okay, which can provide a data rate up to 6 Mbps. Okay, 6 megahertz can provide us data up to 6 Mbps. Now you see your mobile is working at 1.9 gigahertz. Okay, so what speed it can give. While at 60 gigahertz at 1%, thus if you take a signal at 60 gigahertz, then 1% bandwidth will be 600 megahertz, allowing a 600 mbps of data rate. So these are some of the advantages why the microwave engineering applications are so wide. Now let us see what are the different applications. So as I said, communication, it comes to terrestrial and satellite communication. Then it comes to radar application, which comes civilian and military. That means in civil, what are the radar application, and in military, what is the radar application. Next, industrial and biomedical applications are there, and then heating application is there. Okay. Now in civilian, it comes to air traffic control, air navigation, ship safety, safe vehicles, space vehicles, remote sensing, law enforcement. Okay, so all these are comes under the civilian applications. And military application, surveillance, navigation, guidance of weapons, electronic warfare, etc. and C3 is a concept, we will discuss this later. Surveillance, navigation, guidance of weapons means now you see that missiles are being made. So how do the missile gets guided, or how the base station tracks the missile? Based on this radar technology only. Industrial and biomedical, so like process control, drying, canning, treatment of elastomers, waste management, nuclear and cellulosic, monitoring, imaging, and hyperthermia. So all these are different applications of in case of industrial and biomedical. And then heating, industrial and household. In household, the like you have read about the oven, right? Microwave oven. So that is this the household. Okay, now in this video we'll end here with this much of discussion of applications. In the next video we'll see some applications, specifically we'll explain those. So thank you. Please see the next video.